Have you felt that this year's heat is abnormal? That's not your imagination. According to the latest release from the World Meteorological Organization, there is an 80% chance that global temperature records will be broken again within the next 5 years. In other words, it may get even hotter. Airport runways have cracked under extreme heat. The Eiffel Tower itself has expanded, tilting by nearly 20 centimeters. And in the Arctic, temperatures are rising at 3.5 times the global average. But while we worry that Earth may be turning into Venus 2.0, a far more counterintuitive scientific truth remains. We are still living in a long ice age, specifically a relatively warm phase within it. So, when will the next ice age arrive? To answer that question, we must throw you back millions of years into Earth's past to feel the planet's climatic pulse and search for answers written in deep time. Here, you will witness a period both majestic and decisive, one that shaped the future of life on Earth and left behind some of the most astonishing traces we've ever discovered. This was the last ice age. This journey will show you firsthand the extreme environments life on Earth can endure. Over 100,000 years ago, vast ice sheets reshaped ecosystems across the planet, carved by polar winds, defined by barren, frozen landscapes. This was a glacial period of relentless cold, lasting thousands of years. When it finally ended, many iconic species vanished mysteriously, and their disappearance still puzzles us today. This was not Earth's first ice age. In fact, our planet has experienced 5 major ice ages. So what do they all have in common? An ice age is a prolonged period of extreme cold, often lasting millions, sometimes tens of millions of years, during which vast ice sheets blanket large portions of the planet. What we commonly call the last ice age began about 2.6 million years ago, at the start of the Pleistocene. And surprisingly, we are still in it today. Every ice age includes 2 alternating phases, glacial periods and interglacials. We are currently living in the latest interglacial, the Holocene, which has lasted about 11,000 years. So when people refer to the last ice age, they usually mean the last glacial period, which lasted from roughly 115,000 years ago until 11,700 years ago. Here's another surprising fact. During the last glacial maximum, global average temperatures were only about 6 degrees Celsius colder than today. But even a few degrees of global change can completely transform the planet. A 6-degree drop represents an enormous loss of heat across the oceans, land, and atmosphere. At the height of the Ice Age, much of Europe and North America was dominated by 2 colossal ice sheets, the Laurentide Ice Sheet and the Fenno-Scandinavian Ice Sheet. Vast amounts of Earth's water were locked in ice, causing sea levels to plunge. The land was dominated by tundra vegetation and dry grasslands. No single factor explains why Earth entered such extreme cold, but when we examine Earth's orbit, many mysteries begin to resolve themselves. In the early 20th century, Serbian scientist Milankovitch proposed a groundbreaking theory. Long-term changes in Earth's position and motion drive major climate shifts. Milankovitch identified 3 key cycles that alter how much solar energy Earth receives. These are now known as the Milankovitch cycles. First, orbital eccentricity. Gravitational interactions, especially with Jupiter and Saturn, cause Earth's orbit to shift between circular and elliptical shapes over a roughly 100,000-year cycle. When the orbit becomes more elliptical, season lengths change dramatically. Earth reaches its farthest point from the Sun in July, receiving about 23% less solar radiation than in January.
Winters become milder and shorter. Summers become cooler and longer. Second, axial tilt. The tilt of Earth's rotational axis varies over 41,000 years. Greater tilt means more extreme seasons. Less tilt means gentler ones. When the tilt is small, summers may not be warm enough to melt winter snow, allowing ice to accumulate and potentially trigger an ice age. Third, axial precession. Earth's axis slowly wobbles like a spinning top over a cycle of about 26,000 years. This alters seasonal contrasts, making them either more or less extreme. Together, these cycles shape Earth's long-term climate. They are remarkably reliable at predicting major ice ages, but shorter-term events can amplify or disrupt them. During the last ice age, sudden warming episodes, known as Dansgaard-Oeschger events, were punctuated by rapid cooling events called Heinrich events. This raises a crucial question. How did the creatures roaming Earth at the time survive? What did they look like? How did they live? The Ice Age was truly the age of giants, and giant is no exaggeration. Some animals weighed over 4,500 kilograms. Why did life trend toward gigantism? One explanation is Bergmann's rule. Warm-blooded animals tend to grow larger in colder climates because larger bodies lose heat more slowly. This may help explain why the Ice Age produced so many awe-inspiring giants. Let's begin with the most iconic of all, the woolly mammoth.
For most of us, the mammoth is the ultimate symbol of the Ice Age, a towering, majestic figure moving slowly through vast fields of snow, seemingly immune to the cold. But the reality was more nuanced. Despite their imposing presence, woolly mammoths were not significantly larger than modern elephants. Skeletal measurements show their shoulder height averaged around 3.5 meters, while some male African elephants today can reach 4 meters. Size alone was not their greatest advantage. What truly set mammoths apart were their adaptations. They possessed a dense two-layer coat, a thick, woolly underfur covered by long, coarse guard hairs that shielded them from wind and snow. Beneath that fur lay a substantial fat layer, up to 9 centimeters thick, providing insulation and energy reserves. Their bodies were shaped for the cold, longer torsos, shorter legs, and small fur-covered ears that minimized heat loss. Even their curved tusks served multiple purposes, clearing snow to reach buried grasses, defending against predators, and competing for mates. These were not just survivors, they were specialists, finely tuned to one of the harshest environments Earth has ever produced. And yet, despite all these advantages, the mammoth did not last. Their extinction was not sudden, nor universal. Across most of their range, mammoth populations declined as climates shifted and habitats fragmented. But in one remote place, they endured. On Wrangel Island, a small population, perhaps 500 to 1,000 individuals, survived long after their mainland relatives vanished. They lived on this Arctic island until around 4,000 years ago, more than 1,000 years after the Great Pyramid of Giza was built. Their final disappearance was likely the result of a fragile balance breaking, limited genetic diversity, environmental stress, and the growing presence of humans. The mammoth story teaches us something profound. Even the most perfectly adapted species can vanish when conditions change too quickly. But mammoths were not alone. The Ice Age gave rise to creatures even more unusual, animals so strange they seem almost mythical today. Among them were the glyptodonts, massive, heavily armored mammals, relatives of today's armadillos. Some weighed over 2 tons, walking on pillar-like legs across the plains of the Americas. Their bodies were encased in enormous bony shells, like living tanks, making them resemble giant prehistoric turtles. Though they appeared slow and cumbersome, recent studies suggest they could rear up on their hind legs, using their heavy, club-like tails as powerful weapons or to reach higher vegetation. These were not passive animals. They were formidable survivors in a world where size and resilience meant the difference between life and death. Another group of Ice Age giants may surprise you, because their descendants still live among us today. But compared to what once existed, modern forms are only a shadow of their former diversity. During the late Pleistocene, sloths were not tree-bound, slow-moving creatures. They were among the most widespread and successful mammals in the Americas. More than 27 genera existed, with countless species roaming from North America to South America. Over time, sloths followed the Ice Age trend. They grew larger. By the late Pleistocene, nature produced a group now known as giant ground sloths. Some species combined the height of a giraffe with the mass of an elephant. One of the earliest known sloth fossils, Megatherium, is estimated to have weighed up to 3,800 kilograms. Compared to these giants, modern sloths appear almost delicate, a reminder of how drastically life has changed since the Ice Age ended. Yet, perhaps the most astonishing discovery is not their size, but how they lived. Across parts of South America, scientists have uncovered vast tunnel systems.
Burrows carved directly into solid rock. Some are large enough to walk through upright. Based on claw marks and structure, researchers believe these tunnels were dug by giant ground sloths, animals weighing between 800 and 1,200 kilograms. Why would creatures of such immense size dig underground? Some scientists suggest it helped them retain heat in cold climates or escape extreme temperatures during warmer periods. Others believe the burrows offered protection from predators, and that raises an unsettling question. What kind of predator would dare hunt a giant ground sloth? The answer may include saber-toothed cats or the massive short-faced bears, among the largest carnivorous mammals to ever walk the earth. In this world, survival demanded size, strength, and adaptability, yet even that was not enough. As the Pleistocene drew to a close, something remarkable happened. Across continents, giant animals began to vanish. In Australia and the Americas alone, between 72% and 88% of large animal species went extinct. This disappearance was rapid, widespread, and deeply puzzling. Why did animals that had survived multiple glacial cycles suddenly collapse? For nearly a century, scientists have debated the answer. One explanation points to climate change. As the Ice Age ended, ice sheets melted, sea levels rose, and land bridges disappeared. Habitats shifted faster than many species could adapt. But this theory has a problem. Some megafauna, like the mammoths of Wrangel Island, survived long after these changes. So researchers turn their attention to another possibility, one that places us at the center of the story: humans. At this moment in Earth's story, your journey reaches a turning point. For the first time, you come face to face with your own ancestors, Homo sapiens. Our species evolved in Africa around 300,000 years ago. Over time, small groups migrated outward, eventually spreading across the globe. This means humans lived through much of the Pleistocene, sharing the planet with the Ice Age giants. And this coincidence in time raises an uncomfortable question. Were we responsible for their disappearance? At first glance, the idea seems unlikely. How could relatively small, poorly armed humans bring down creatures like mammoths or giant sloths? One human alone would stand little chance, but humans rarely acted alone. By the late Paleolithic, our ancestors had undergone a cultural transformation. Hunting and gathering became more sophisticated, toolkits diversified, symbolic objects appeared. Pendants, pigments, carvings, signs of abstract thought and shared identity. Most importantly, hunting technology advanced. Long spears with stone tips could be thrown over distances of up to 40 meters. This changed everything. A single hunter was vulnerable, but a coordinated group, communicating, planning, driving prey, could challenge even the largest animals on Earth. One of the most famous hunting cultures was the Clovis people, early inhabitants of North America and ancestors of many indigenous Americans. They are named for their distinctive weapons, Clovis points, finely crafted, fluted stone spearheads designed for maximum lethality. Here lies a striking pattern.
Within just a few thousand years of Clovis people arriving in North America, many large animal species disappeared. Correlation does not prove causation, but the timing is difficult to ignore. In recent years, scientists analyzed the remains of a single Clovis child, the Anzac child, buried over 12,000 years ago. Chemical analysis revealed that around 40% of the mother's dietary protein came from mammoth meat. This evidence suggests that mammoths were not rare prizes, they were a significant food source. Taken together, these clues lend weight to the idea that human hunting pushed already stressed populations past the point of recovery. Australia tells a similar story. Soon after humans arrived on the continent, nearly 85% of large animal species vanished. Fossil evidence indicates that megafaunal populations collapsed within 4,000 years of human settlement, despite previous climate fluctuations they had survived before. Once again, human arrival appears to have been the final tipping point. But humans were not the only ones to disappear. Another human species, one remarkably well adapted to cold climates, vanished during the late Ice Age: the Neanderthals.
Neanderthals were not primitive brutes, as they were once portrayed. They were the first humans to thrive in the harsh glacial ecosystems of Ice Age Europe. Their bodies told a story of adaptation. Short, powerful builds reduced heat loss. Broad chests housed large lungs. Wide noses and high nasal bridges helped warm and humidify icy air. In many ways, their physical adaptations mirrored those of Ice Age megafauna, like the woolly mammoth itself. But Neanderthals were more than their bodies. Archaeological evidence reveals a culture far richer than once imagined. They crafted sophisticated stone tools, controlled fire, and hunted large animals cooperatively. They cared for the injured, buried their dead, and may have used language. Thank you for watching Entropy Files.